Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on review of theory of elasticity. See, in this review I will try to highlight certain important aspects of how we solve the problem in theory of elasticity rather than getting into detailed derivations. Whatever the discussion that we do, which will help us to develop the crack tip stress and displacement fields in an indirect manner. This knowledge base is essential for you to develop the solution for the crack problems. And in the last class we have started discussing the solution for the case of a beam under uniformly distributed load. I drew your attention to the fact, when I have a uniformly distributed load, shear force varies along the length of the beam. It is not remaining constant, it is varying along the length of the beam. When shear varies along the length of the beam, your flexure formula is no longer valid. Flexure formula is valid only for the case of constant bending moment. We saw as an exception, if you have a constant shear force, you could use it as an exception, and if you have deep beams, then again there is a shear coupling. And in this case what you find is the shear force varies linearly over the length of the beam. So, definitely the flexure formula is not applicable. The plane sections do not remain plane before and after loading. So, you need to expect a remedy by solving it through theory of elasticity. And another aspect is, while you learn how to draw bending moment diagram, you first take up the case of concentrated forces. You may have a 3-point bend, I may have a concentrated force rather than a distributed loading. But when you solve the problem by theory of elasticity, the boundary conditions could be easily specified when the loading is distributed like this. So, this is one of the simplest problems taken up while developing concepts in theory of elasticity. The reason is the boundary conditions could be specified, and one of the first things you do is, in order to write the boundary condition, you replace the support reactions by the shear loading on the end faces. And this is what is indicated here for clarity. And what is the stress function for this problem? The stress function for this problem is given as phi equal to a2 x squared plus b3 x squared y plus d3 y cube plus d phi x squared y cube minus 1 by phi d phi y power phi. If you really look at, you have certain elements of polynomial of degree 2, polynomial of degree 3 and polynomial of degree 5. These are combined in a suitable fashion to be a valid stress function for a problem that we have taken up. How people arrive at? There are no set procedures. By trial and error people arrive at it, some logical reasoning they would be able to give it, but once the stress function is specified, the entire problem can be solved. And if you look at the stress function, I have the coefficients a2, b3, d3, d5, these have to be determined. I have 1, 2, 3, 4 coefficients, and these 4 coefficients need to be determined. And you look at the boundary conditions, they provide you sufficient number of equations to get the coefficients. And what are the boundary conditions? The origin is taken as the center of the beam. So, you have plus h by 2 and minus h by 2. At h by 2, what you have is you have the distributed load, and we are considering a unit thickness. So, sigma y itself becomes minus q. So, on the top surface you specify the boundary condition, on the bottom surface also you have specified the boundary condition sigma y equal to 0. And we also have on the top and bottom surfaces, that is y equal to plus or minus h by 2, the shear stress is 0. And what other conditions that you can write? You could write what happens on this edge as well as this edge, and that is covered by your overall equilibrium requirements, because what we know here is only the shear force. We do not know what is the distribution. The distribution has to be obtained as part of your solution procedure. So, I can only write on this edge integral minus h by 2 to plus h by 2 tau x y dy equal to q L by 2. That is the only thing which I can write. I would not be able to specify individual magnitudes of tau x y like what I had done on the top face and the bottom face. I know only the integral equal to a quantity like this. And what other things that you have here? There is no force in the x direction, there is no moment, and they also appear as relevant conditions. So, I have integral minus h by 2 to h by 2 sigma x dy equal to 0, the net force is 0, and you also have minus h by 2 to plus h by 2 sigma x y dy equal to 0. So, this gives you the moment, and if you look at the boundary conditions, it is possible for you to evaluate these coefficients. I am not getting into those details, and once you know what is phi, you can easily write the expression for sigma x, sigma y and tau x y. So, we will directly look up what are these stress quantities, and I get sigma xx as q by 8 I into 4 x squared minus L squared y. If you look at like this, it looks as if it is something different. In essence, this is nothing but what you get from your flexure formula. This term is nothing but m y by I. So, I have a part of the solution is same as what we have seen in the strength of materials approach, but there is an additional term which is actually a correction factor, which is given as q by 60 I 3 h squared y minus 20 y cube. So, theory of elasticity recognizes the deformation of the planes, and because we are satisfying the overall equilibrium condition as well as the boundary conditions and compatibility, and finally, we get a solution, because we have not made any assumption on the displacement picture. Displacement is evaluated as part of the solution procedure. So, in a sense, it has expanded the scope of problems that you could solve by theory of elasticity approach. That is the way you have to look at it. Then you have a surprise that I have an expression for sigma y y, which we never saw in strength of material solution. You would not even recognize that sigma y y exists, and that is given as q by 24 I into 4 y cube minus 3 h squared y minus h cube. Then you have tau x y, which is given as qx divided by 8I into h squared minus 4y squared. This is same as what you get from strength of material solution, because shear force varies as a position of x, you have the term qx here, and you will essentially get the shear force distribution as a parabola. So, what you find is there are two quantities which are different. You have additional term for sigma xx, and you also have another stress component sigma yy, because if you have to satisfy the equilibrium condition on the top surface, unless you substitute these quantities however small, it will not go to 0, and this is pictorially represented in this slide. So, you have the cross section of the beam, and you have the bending stress which varies linearly as in strength of materials. You have the shear stress, this is also the variation is parabolic, top and bottom surface shear is 0, and you have the correction term to sigma x. See, this is only a schematic representation, you should not compare the magnitudes of this stress and this may be quite small. In order to visualize the variation, it is drawn big. Similarly is the case for sigma y also. So, you get two additional quantities as part of your theory of elasticity procedure. So, if you take the problem of beam under uniformly distributed load, the complete solution encompasses all these components, and this is only the correct solution. What you have got in strength of materials was only an approximation good enough for engineering analysis. We are not making serious error by neglecting the correction term to sigma x or not incorporating sigma y. And another aspect also you can keep in mind, see, I said you have been able to solve comfortably a problem of distributed load on the beam, because I could specify the boundary condition easily, and my stress function was also very simple. I had only combination of polynomials, certain terms of the polynomials were selected and put, we were able to get the solution, and it coincided with central material solution on few aspects. So, that way you find that we are in the right direction and so on and so forth. Suppose I want to solve the problem of a beam with a concentrated load at the center, that means 3-point bending. We have seen already you could have Fourier series as a candidate for constructing stress functions. You would in fact have to do by taking several harmonics, and when you solve the problem you will come out with a very interesting aspect. See, in this case we have seen shear varies parabolically over the depth of the beam. In the case of a concentrated load, as you go closer to the concentrated load, the shear will not vary parabolically, because you have a concentrated load on the top surface, shear just below the surface will be very high and it will diminish to 0. The overall shear force would remain same, that there is no confusion, but the shear force distribution will be drastically different, and you can look at book by Timoshenko where he has written pages after pages how to solve the problem of a beam under 3-point bending, and one of the significant result there is shear variation is different as you go close to the points of loading, and unless you take care of that in your design scenario by providing extra reinforcements, your beam will fail. So, what you will have to keep in mind is strength of material has provided certain level of knowledge, but if you want to proceed further you need to improve your method of solution, and that has been reasonably achieved by theory of elasticity. And we have looked at the problem in Cartesian coordinates earlier. Now, we look at the problem in polar coordinates. What is the nature of biharmonic equation in polar coordinates? And we will define what is del squared. So, del squared sigma r plus sigma theta equal to 0 is the compatibility condition, and del squared is given as dou squared by dou r squared plus 1 by r dou by dou r plus 1 by r squared dou squared by dou theta squared. See, in fact, when we take up the problem of crack in an infinite plate, we would first solve by Westergaard's approach in arriving at the stress field equations. The Westergaard's stress field equation is constructed based on Cartesian coordinate system, and you would use essentially analytic functions for arriving at the stress and displacement fields. Later, we would also look at Williams methodology for crack problems. That approach is actually done in a polar coordinate system. So, learning this is equally important. Another reason why I cover this polar coordinates is, in fact, many problems of common interest you find solution from polar coordinate system. The moment you define what is phi, the expression for sigma r, sigma theta theta and tau r theta are specified like this, and sigma r is given as 1 by r dou phi by dou r plus 1 by r squared dou squared phi by dou theta squared, sigma theta theta as dou squared phi by dou r squared, tau r theta equal to minus dou by dou r of 1 by r dou phi by dou theta. In fact, you should be able to remember these expressions by looking at the mnemonic way of understanding them. If you look at Cartesian and polar, by looking at them again and again, you will know how to remember this, because they are very fundamental quantities. So, the idea here is, whatever we have learnt in Cartesian coordinate, the knowledge would help here also. You have this del squared is given in this fashion. Once phi is specified, you could find sigma r, sigma theta and tau r theta. Now, let us look at what are the forms of stress function in polar coordinates. It is very similar to what we have looked at in Cartesian coordinate system. We have looked at, in Cartesian coordinate systems, I could have polynomial functions, I could have Fourier series, I could have analytic functions as candidates for coining stress function. In the case of polar coordinates, the generic form is phi equal to function of r multiplied by cos n theta or sin n theta. You are not taking a very generic expression in terms of theta, you could have a general function in terms of r, and this kind of a combination is found to solve a variety of practically important problems, and we will look at each of them case by case. Now, you have the case 1 where you are talking about axisymmetric problem, and here n equal to 0. One of the very famous problems in this category is the problem of a thick cylinder. For thin cylinder, you know PR by T, PR by 2T you are able to develop, but when I have a thick cylinder, you have to go by theory of elasticity, and you have the stress function for this is given as A r squared natural logarithm r plus B r squared plus C natural logarithm r plus D. And in theory of elasticity, if you come, for each of these problems a name is attached. He was the person who has solved this problem first, and this is known as a Lami's problem. And you have a thick cylinder, the wall thickness is considerable, and if you have to find out, you will have to go by theory of elasticity. And what is the kind of domain here? We have discussed what are simply connected and multiply connected objects. It is actually a multiply connected object, and in this case just satisfying the biharmonic equation and boundary condition alone is not sufficient. You should also look at whether the displacement is unique when you go around the ring once. That kind of argument is necessary to make the coefficients a 0. So, if you recall how you have solved the Lami's problem, you would say the coefficient a has to be 0 by looking at the displacement picture. It is very important. See, in theory of elasticity, we keep saying we are not making any assumption about the displacement. Certain aspects of displacement information need to be used for the solution procedure also. So, this is one category of problem you can solve using this. The other category is, please try to make a neat sketch of this. The same stress function could also be used for initially curved beam in pure bending. You have very many practical applications where initially the beam is bent. Suppose you want to analyze a crane hook, it is subjected to shear as well as bending moment. So, if it is subjected to shear, we have to use another stress function to solve it. Then linear superposition is possible, because we are living in the linear elasticity domain. So, superposition is possible. It is a very useful technique. In fact, superposition is a useful concept when you have linear elasticity. The same idea we would also extend it for linear elastic fracture mechanics. So, principle of superposition is one of the very important tools. So, you could go and get the solution for initially curved beams with the same stress function. So, what will happen is the coefficients will differ. It is depending on the loading and the boundary condition of the specific problem. And you can also construct another set of stress functions. First we saw the case n equal to 0, we label that as an axisymmetric situation. Now we go to the situation where n equal to 1, we have already seen a generic form of stress function. So, that would be rewritten as phi equal to f1r cos theta. Instead of cos n theta, n has become 1 here. So, it is cos theta, or you can also have f1r sin theta, function of r into sin theta. And the function of r, why we put this as 1 is because we have also written the generic situation f suffix n. We are now talking about n equal to 1. So, it becomes f suffix 1. So, the function of r is taken as a1 r cube plus b1 by r plus c1 r plus d1 r ln r, and this is the useful stress function to find out the stresses due to shear loading of curved beams. These are all problems that we come across. You cannot avoid them in actual engineering practice, and some of the solutions we have been using it all along, and actually it comes from theory of elasticity analysis. We have seen n equal to 0, n equal to 1, the next step is n equal to 2. So, what you find is n equal to greater than or equal to 2, you have a generic expression where phi is defined as FNR cos n theta or FNR sin n theta, and the generic function f of r is given as a n r power n plus b n r power minus n plus c n r power n plus 2 plus d n r power minus n plus 2. This is a useful stress function to solve the problem of a plate with a small hole, infinite plate with a small hole. See, I am discussing this problem using a finite screen, so I have to draw a finite diagram. So, when n equal to 2, the stress function is useful to solve the problem of stress distribution in the case of a small hole in an infinite plate subjected to uniaxial tension. We would also see some aspects of the solution more from the point of view of appreciating the principle of superposition. Quite a good variety of problems you have been able to solve by taking stress function in this nature. There are also other forms of stress function. You have phi defined as c r theta sin theta. The function of r is simply r, but the function of theta is slightly involved. And you could have another stress function which is defined as c r theta cos theta. It is a very useful stress function. Many problems which are of practical interest could be solved. I think I would enlarge this figure for you. What you have here is, I have a concentrated load on a semi infinite plate. You have an infinite boundary here, I have a concentrated load, I have a load at an inclination, I have a load which is tangential to the surface. And if you look at the diagram carefully, the same stress function c r theta sin theta or c r theta cos theta could be invoked for all these three cases by carefully defining theta. Theta is defined from the reference point as the loading. Loading is horizontal, you measure theta from this, loading is vertical, measure theta from this, loading is inclined, measure theta from the axis. So, if you recognize this, you get a family of solutions for important problems just by redefining how you measure theta. For all these cases you get solution. And if you look at the concentrated load, this is like your Boussinesq problem. Then you have extension of this. If you look at the contact stress analysis, it all started from this basic solution of Boussinesq, which is extended by Hertz, and you have Hertzian contact problem. And we have also looked at how to find the solution for a disk under diametrical compression. That also comes from this basic solution. From this as the basic solution, you could find the solution for the case of a disk under diametrical compression. So, it is a very useful solution, and you would also be able to find out for the case of a wedge problem, the same stress function is useful. And where do you find the application of wedge problem? Suppose I want to analyze a cutting tool. The cutting tool is removing metal while you do the machining operation. If you want to analyze the cutting tool, the wedge problem could be invoked. So, from a practical point of view, quite a nice set of problems could be solved by looking at the stress function in polar coordinates. So, polar coordinate is very useful. You find very many practical problems you could solve from stress function expressed in polar coordinates. We will now look at the problem of infinite plate with a small circular hole, just the highlight of it. I will not get into the complete solution. And as I mentioned, for any of the problem in theory of elasticity, a name is associated. For this problem of a circular hole, it was Kirsch in 1898 who solved it, and this is known as a Kirsch's problem. And since we have a nice facility for animation, for illustration I have taken it like this. You have an infinite plate with a small circular hole that could be visually appealing, but when I want to do it in a finite domain, I have to take a finite diagram, and in order to see what kind of things I represent in the hole, I make it bigger. Because one of the common confusions I have come across in students is they do not recognize that theory of elasticity provides solution only for an infinite plate with a small hole. Because you are accustomed to seeing a finite diagram like this in the books, the students immediately jump when they actually solve a problem of a plate with a hole which is finite in dimension. They think that this solution is directly applicable. Because of space constraint, you have this. You have to imagine that the boundaries are at far away distances from the whole dimension. And there are other things that also we do. Though the problem is like an infinite plate, rectangular plate with a small circular hole, one of the methods of solution is look at this as a boundary which is in circle in nature at infinity, and rewrite the boundary condition. You have only sigma xx, this stress components could be rewritten as suitable boundary condition for a circular plate. And why we take up this in a polar coordinates? I have the circular hole and I also have the outer boundary as circle. It is convenient for me to specify the boundary condition if I look at the problem in polar coordinates. And this is what I mentioned, when people wanted to solve for the problem of a elliptical hole, they needed to develop elliptic coordinate system, because they have to specify the boundary condition on the boundary of the elliptical hole. And polar coordinate system is lot more simpler. That is the reason you find a infinite plate with a circular hole was solved first. And we will also have a brief look at the principle of superposition employed, and before I get into that, you have nice set of fringe patterns that are formed because of photoelasticity, and this is for a finite plate. Do not confuse this, this is for a finite plate with a hole, not for an infinite plate with a small hole. So, what we do is we are using Saint-Venant principle. The small central hole will not affect the stress distribution at distances which are large compared to the diameter of the hole. So, I take R is much greater than A, but pictorially it is represented in this fashion, but mathematically you recognize R is much larger than A, and this is the kind of stress field that you have, and we would get that from the stress tensor. Stress tensor is given as sigma xx 0 0 0, it is a 2-dimensional problem, and what we will do is we will replace this whatever the far field stress as appropriate boundary condition on the boundary of the hole, and which you could do it by suitable stress transformation. So, I have the direction cosine matrix, I am taking a generic section at theta, between r and x it is cos theta, between r and y it is sin theta, between theta and x direction it is minus sin theta, between theta and y it is cos theta. And we know what is the stress tensor. I can find out the stress tensor in polar coordinates by simply multiplying the direction cosine matrix. So, you have this as A and this as A transpose. So, you have this as cos theta minus sin theta cos theta. So, what we are doing in this step is we want to recast the problem as the outer boundary being circular for facilitating a solution procedure. See, there are also other methods of solution. People have taken the outer boundary as rectangle and they have also proceeded. That is also another way of doing it. But this is all another method which is far more simpler, and my interest is to show that how we use the principle of superposition to arrive at the solution. My focus is only on that, because if I have to go to the level of superposition, I must look at the stress components on the boundary of the hole and then recast the problem. So, from the expression we would be getting sigma RR as sigma XX divided by 2 into 1 plus cos 2 theta, and then tau R theta as minus sigma XS by 2 sin 2 theta. I think you can take some time to plot this nice picture. So, whatever you have as the boundary condition on this hole could be thought of as superposition of two problems. Here I have sigma XS by 2, look at this as a annular plate with sigma XX by 2 acting uniformly all over the boundary. This is one problem. For this you already have a solution, this is nothing but your Lami's problem. And you have another problem, I have shown only one loading, I have shown the loading of sigma XX by 2 into cos 2 theta, make a sketch of it. The pictorial sketch is very interesting, you may not find in many books. In addition to this, you also have the shear stress tau R theta, that also we will show. After you have drawn this, we will look at how the variation of minus sigma XX by 2 into sin 2 theta appears. Maybe if you want I can make this big. So, this is what you have. You can draw it on the boundary. So, this denotes positive values, these denote negative values, that is the symbolism that is used. And we will also look at the shear stress. The shear stress variation would be something like this. And this is minus sigma XX by 2 sin 2 theta. So, you have both these kind of loading exist in this problem. You have contribution from sigma XX by 2 cos 2 theta and minus sigma XX divided by 2 sin 2 theta. So, what we have looked at is, we have looked at the problem of a small hole in an infinite plate, infinite rectangular plate is recast as small hole in a circular plate, and we have suitably looked at the boundary condition. By looking at the boundary condition, we were able to split this into two sub problems. One problem is your conventional Lami's problem with a specified loading, the loading is different here, but that loading we have seen now. The other problem is you have the stress components sigma XX by 2 cos 2 theta and sigma XX by 2 sin 2 theta. And if you look at the nature of the stress function, it is in the form of sin 2 theta and cos 2 theta. So, that is the reason why you are able to take that kind of a stress function. We have said n equal to 2 is a good candidate for solving the problem of a plate with an infinite hole. So, you solve this problem using that stress function and add these two. When I find out sigma x x, component 1 here, component 2 here, you could add them, because we are living in the domain of linear elasticity. In linear elasticity, one of the very powerful methodology is principle of superposition. In fact, when we look at certain solutions for finding out stress intensity factor in fracture mechanics problems, we would employ principle of superposition and evaluate the stress intensity factors, because there again we are going in for a linear elastic fracture mechanics. So, that is the reason why I thought that I should emphasize principle of superposition has been used even in your conventional theory of elasticity approach. It is not something new. The strength comes from your linear elasticity, that is what is important. Then you could also have a look at the elliptic coordinates. I will just show the elliptic coordinates, and you have to recognize that these were necessary for solving the problem of a plate with an elliptical hole, and this comes from a basic expression x squared by cos squared alpha plus y squared by sin h squared alpha equal to c squared, and for different values of alpha one gets confocal ellipses. These are shown here. I could also zoom in and then show you have confocal ellipses. So, when you specify what is alpha, you define the boundary of the elliptical hole. So, it becomes convenient to specify the boundary condition, and this is what I emphasize in the early development of theory of elasticity. When they had to solve the problem, parallelly they had to develop suitable coordinate system also. Skewed plates are used in aerospace structures. So, they developed skewed coordinate system, and if they have to analyze sphere, they had developed spherical coordinate system and spherical bipolar coordinate system, and these were all important research contributions in those days. So, without suitable coordinate system, they were unable to attack problems that come across in actual practice, and this is where your finite element solutions, which are basically numerical in approach, provided a via media to handle complex boundaries, at least approximately. So, that is the advantage of your numerical techniques. So, if I have to solve a problem by analytical approach, I need to develop suitable coordinate system as well. So, you specify alpha equal to a constant and then find out what is the inner boundary of the ellipse, and you have alpha and beta. You essentially get sigma alpha alpha and sigma beta beta, that you interpret as suitable quantities for your data interpretation. So, what you have is semi major and semi minor axis of the elliptical hole are given as A equal to c cos alpha naught and B equal to c sin h alpha naught. So, this provides you a comprehensive overview on certain aspect of theory of elasticity. We have looked at the Cartesian coordinate system as well as the polar coordinate system, and the moment you get the stress function, you are in a position to arrive at the solution. So, the starting point is the stress function. How people get the stress function is a very challenging aspect. See, before we take up the issue of developing crack tip stress and displacement fields, I said analytic functions are used to coin the stress function in fracture mechanics. That is what Westergaard has used. So, we need to understand what are analytic functions. you know, if a function is analytic when it is having a derivative. The derivatives of a function of a complex variable w equal to f of z is defined by dw by dz. You have a similar notational interpretation. You put w prime, if you put 1 prime, it is dw by dz equal to f prime z is given as limit delta c tends to 0. You evaluate the function at z plus delta z minus f of z divided by delta c. So, now we will have to look at, for you to get this differential, what are the finer aspects that we will have to look at. And z is a complex number, z equal to x plus iy. So, what you will have to keep in mind is, for the derivatives to exist, no matter how delta z approaches 0, it is necessary that the limit of the quotient be the same. So, that has to be ensured. So, you look at this function w as a real part u x comma y plus imaginary part given as I into v of x comma y. The real part is u x y, imaginary part is v x y. And we have already said we want to find out whether the derivative exists. So, dw by dz, the definition is limit delta z tends to 0 delta w by delta z. So, you could have delta z is real, in that case delta y equal to 0. You could have delta z is imaginary, in that case delta x equal to 0. So, no matter how delta z approaches 0, that is depicted in the graph here. So, you have in the first case delta x equal to 0, delta z equal to I delta y. So, it varies like this. The second case you have delta y equal to 0, delta z equal to delta x. So, it varies like this. You could have a case where both delta y and delta x changes. So, they are related like this. It is a linear relationship, or it could also move in a curve. So, now what we want to ensure is, whichever way delta z approaches 0, I must have a unique value of dw by dz, which enforces certain conditions between the real and imaginary part forming the complex function. These conditions you have developed, you have to know what is the reason behind it, because whichever way delta z goes to 0, I must get one unique solution. And now we will take case by case. We will take the case that delta z is real, and we want to write what is dw by dz. And what is dw by dz? It is nothing but, in the limit delta x tends to 0, you have to calculate u of x plus delta x comma y plus I v of x plus delta x comma y minus u of x comma y plus I v of x comma y divided by delta x. And these could be grouped as real and imaginary part, that is what the way depicted in the next step. And these could be written comfortably from the basic definition of how do you write differentials. You are having this as u of x plus delta x comma y minus u of x comma y. So, this I could write it as when the satisfy the limit delta x tends to 0, I can simply write this as dou u by dou x. I can simply write this as dou v by dou x. So, what you get here is dw by dz becomes equal to dou u by dou x plus I dou v by dou x. We are taking a case when delta z is real. Now, we will take the case when delta z is imaginary, and we will write the same thing. Let us see what we get. So, here you have to carefully write this as limit delta y tends to 0. So, that means x plus I delta y is what we are looking at, and x is 0 here. So, you have this as I delta y coming to the picture, and suitably these expressions are written. Here again you write the generic expression, then segregate them by real and imaginary parts, and you could comfortably write this as 1 by I dou u by dou y, and you will have this as dou v by dou y. So, what I get here? I get this as dw by dz equal to 1 by I dou u by dou y plus dou v by dou y, or in other words it is actually dou v by dou y minus I dou u by dou y. So, now I have two expressions for dw by dz, they cannot exist like that. So, there has to be some interrelationship between the real and imaginary parts. We will continue that in the next class. So, in this class what we have done is we have done a brief review of theory of elasticity, and towards the end we have looked at what are analytic functions. All this have been developed in your courses on mathematics, because you have lost touch for a long time. It is desirable that we review them and take up evaluation of stress fields in the case of a plate with a crack.